And welcome back to the Empowerment Project. This is specifically a session discussing a kind of procedure in R called aggregate. To tell you about aggregate, first I'm going to tell you about this experiment. The experiment is answering this question: what is the role of compost in soil moisture in an urban agriculture setting? In collaboration with Mission of Mary Farm, several years ago, a student in my research lab did an experiment to test the role of compost on soil characteristics in an urban agriculture setting. You may be surprised to hear this, but you can do research in urban agriculture. It's not supported at the University of Dayton, but it is an exciting area for science, actually. Compost is an important amendment often used in urban agriculture, and we wanted to test how it influenced soil conditions. In this experiment, we added compost at various depths to the top of soil in planted beds, and then we measured the soil. We hypothesized that adding compost would increase soil fertility and help preserve soil moisture. This is a real experiment using real data. By the way, I understand that I'm not in presenter mode or whatever. You'll see why in a second. Just roll with it. This is a real experiment using real data. We will work in this session, and it's our session, with the soil moisture data. The specific hypothesis would be that increasing compost will increase soil moisture. This is the experimental design. There are 3 replicates and 4 treatments: none, 1, 2, and 3 inches of compost on top of the soil. So we had 3 replicates of 4 treatments. Each square was a plot. And this was what's called a completely randomized design. That means that for any plot, you could be given any treatment. The way that it is drawn here is for simplicity. The plot is the experimental unit. So let's assign the plots to this experiment. And I will pull up a website. It's the best website. Random.org. So what we can do is do an integer generate. Actually, we can just do it right here between 0 and 4. And we could assign each of these plots, and we'll just go along this way and say, and 0 is none. And then we can call this would be, this would be the 3 inches. That will be number 1. This will be number 2, and this will be number 3. So it'll be between 0 and 3. And we can just say, okay, generate a random number, and we'll assign that treatment to this spot. Ready? You see it? What's the integer? 3. Okay, this is going to be number 3, we said. So we'll put it there. Okay, ready? It's getting exciting. I wonder what's the, well, this is freaking out. Sorry about that. Let's just work a little bit better. I wonder what this one will be. Ready to go? 2. Okay, 2 is going to be this. Okay, and then we'll go along. I'm not going to do every one because it's too annoying, but that's how you would assign the treatment. So we'll just say, oh, this one is 0. This one is 0 again. And this doesn't have to be in any particular order. We just have to put these out here somewhere. So they're all in different places. It can be like this, and it's going to be right here, and then this one can be right there, and this can be right here, and this one can be right there, or whatever. It doesn't really matter. Okay, the whole point was you just go along and assign a treatment to each of these things. That's a fully randomized design. And so this one would be the heaviest one, which would be the 3 inches of compost. This would be 2 inches. This would be 1 inch. This is no inches. Okay, that's the design. Now, in addition, let's just take all this. And so what we did was we had 5 samples in each plot like this. Whoops, I need to print the front. pretty fun. Oops. Oops, sorry. A little bit of trouble finding my treatments. I should have done this beforehand. I thought it might be useful for you to see what I was doing. There we go. So each of these little blue things would be the sample. And then we would take the samples, 5 samples like that from every plot. And then those samples would be the sampling unit. And then we'll take the average of those samples, and that will be how we sample each of the replicates, right? The box is the experimental unit, that is to say the plot, and this is how we would sample it: 1, 2, 3, 4, 5, and then we take the average of whatever variable we're measuring in that, and then that would stand for that plot, and the experimental unit is the plot, and so the replicate is 3. So this is n equals 3. N equals 3 replicates per treat unit. Okay. Everything clear? Understand the design? Good to go? This is a real experiment too. It's exciting to work with real data. Now let's move over to R and run the statistics. So I will share with you the data set. It'll be called soil. I'll write the CSV because this is not going to work otherwise. Excuse me. We can take a quick peek in soil. It's a big data set. You'll see this is a real research project. Hey, urban agriculture research. And then this is a large data set. For the purposes of this exercise, we're going to only focus on one date in the data set, which is December 6th. So we went out and sampled these things on many different dates. April. I think it's not showing all. Yeah, it's not showing all of the rows. There's 464 rows. There's a lot of data you're not seeing. There's a lot of data here. We're going to focus on, and I think maybe this is something to do with RStudio. It doesn't show all the data, but in any case, we're going to focus only on one of those dates, which is December 6th. We can choose any other date and follow the same analysis approach. We're going to focus on soil moisture. There are other parameters of interest in the data set. We can see, I think there's conductivity, there's moisture, temperature, and conductivity. There's 3. So first, to do the analysis, we're going to take a subset. So to take a subset, we're going to do it like this. December 6th equals subset, open parentheses, soil, that's the data set, comma, date equals, quote, 6-DEC, quote, close parentheses, and run. And then we can see to make sure the data are available. Here we go. This is the head of the December 6th data. Right here, we can look at it a little bit closer. You can see the whole data set if you'd like by just typing December 6th. You should always ask R if it sees the data. Do you see the data? Okay, good. Here are all the December 6th data. This is a real experiment. Here's soil moisture right here. That's the variable of interest. Note that there's other variables. And TRT is the treatment that is none, 1, 2, and 3. And that is the what we're going to analyze. So now we'll make a we'll follow our procedure, our analysis procedure. First, doves, of course. And so we'll generate our normal box plot with the dots, which I affectionately call a Borth plot. This is the Borth plot for the experiment, so you can take a look. None is here. Remember my experiment I just described? 1. But 3 and 2 are flipped here. We're going to have to fix that. We want 3 to be after, but it's just alphabetical. And 2. And so we can start to go through this and look at distribution. Do we see any skewed distributions? No. Outliers. There's one outlier here. Otherwise, no. Variance, it looks like more variance in this set maybe than the others, but equal variance is probably okay. I'm not too worried about it. Effects, well, we do see 3 seems to be lower than the others. So that looks like you've got something. And if you just like think about this box, see my cursor? This box is all the way below that box. Looks like an effect. And then, yes, sample size. So here's the sample size, and now we can proceed with our analysis, correct? Ready to go? If you don't, if you didn't get the willies or like an alarm go off in your head, like a klaxon, that klaxon, when you solve these points, the sample size, you need to stop, and you have to do some work. Go back to the PowerPoint and read the experimental design again. So just go ahead and pause the video and do that. Okay, you're back. What did you see? Because when you see this, when you do the Doves analysis and you see these points, you should have gotten an alarm. You should have been like, what? Now, hold on a minute. What? This doesn't seem right. Because it's not right. This is, each of these is the sampling unit. There are 15 dots here. We can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dots. Those are the sampling units. Remember, the replication is n equals 3. Remember that? You can't have this analysis go forward. If you do, you have done an invalid data analysis. This is, the replication is n equals 3. So now we've got a problem. Okay, we got the data set, but we've got all the sampling units, not the experimental units represented here. So we're going to have to fix it. So S in your Doves analysis should have saved you here from terrible embarrassment and or just lying to people because you did your analysis wrong. What we're going to do is aggregate. Use a function called aggregate. Aggregate is a way, actually, if you work with large data sets, it's extremely powerful. One of the things that's really powerful about R is that R doesn't really care how many rows of data you have. You can have 10,000 or 10. It's the same. The code is the same. And so you can use aggregate to do things that in Excel, for example, you just can't. Or you could, but because I did a lot of data analysis in Excel before R existed. And SAS was not really, there was other software really wasn't capable. And it's can be enormously challenging if you have big data sets. So aggregate is a really important function for doing data preparation. You've got raw data, now you got to get your data ready for analysis. This is a good one for you to know. This is the way to do aggregate. I'm just going to make a new data set. It's going to be ag December 6. That's aggregate December 6 equal aggregate. That's the command. Open parentheses. December 6, that's the data set. Moist is the variable of interest in this case. And we're going to say by equals list, open parentheses again. December 6 is a data set. Oops, I messed up. December 6 is a data set. $sign TRT is treatment. This is what we're going to aggregate by. December 6 rep, that's the replicates. So treatment, replicates in the treatment. And the function is the mean. The function is the mean because we're going to take those 5 samples we've taken and take the average of those, and those are going to represent the experimental unit. Aha. Okay, let's run it. Pause the video, run the video, or run the code, pause the video, and run the code. It will work. If you get any red stuff down there, you just got an error in the console. Now, to take a look, you always should look and see what happened. Ag December 6th. That's aggregate December 6th. Oh, this is a much smaller and simpler data set. because now we've aggregated the 5 samples. Instead of having 15 in each one, now we have 3 in each one. So yes, it should be a lot simpler. When you do the aggregate function, it makes a weird column heading. So we need to rename those column headings. And the way you do that is like this, column names. That's another function, a new function in R. Column names, open parentheses, ag6 is a data set, equals, C is concatenate, we've used it many times, open parentheses, and then we can name it whatever. We're going to go treatment, replicate, moisture, because that's what these 3 things are. Treatment, replicate, moisture. And the moisture is the mean. All right, ready? And now we can look again at the data set like this. And you will see treatment, replicate, moisture. And now we have the correct sample size. Yep, get rid of this. Now let's look at it aggregated. This is the same code as before, except we're pointing to ag December 6th, and X, because we've changed the column names are a little bit different now. We've named them treatment and moisture, so that's what's going to be here. So if you run that, we get this. Aha! Now this makes sense. It should be n equals 3. Remember, that's the experimental sign. Now, here's a different way to look at it. This is a nifty little bit of code. If you can make this work. Uh-oh, no. Here we go. Jeez. There we go. This is pretty sweet. So here's what I've done, and see if you can make this code work. Here, I'm saying GGPlot brackets plus, and then I've written code for 2 different graphs because I'm pointing at 2 different data sets. This one's pointing at the ag6 data set. This is pointing at the original data set, which is December 6th. And in the ag6 data set, each of these 3 points is going to be the mean of the 5 taken from that replicate. In this case, the replicates are the sample units are all displayed. So there's 15 maroon, faded maroon points, and there are 3 black points. The 3 black points are the points that we're going to use in the analysis. The faded maroon points are the sample units. So this graph shows you exactly what was going on and how the sampling units represent the, or how the replicated average values represent the sampling units. See if you can make this graph. You have to have a plus right here to connect the 2, but this is just basically the code for a graph, but the GGPlot part of it, we put it by itself up here. Type the code, run the code. This is very nifty code figure making. And if you get this part figured out, the GGPlot by itself, and then you can make whatever kinds of graphs as long as they share axes you want. This is a nice bit of code for you to know. Now, again, we said before, none, 1, 3, 2 does not make sense on the x-axis. So let's rearrange those. And we're going to rearrange those using a thing called factor. So I'm going to say, okay, agriculture treatment, I want you to factor that agriculture, and we're going to just focus on the December 6th aggregated data. Aggregated data, December 6th treatment, factor that, open parentheses, treatment, same thing, by levels C, none, 1, 2, 3. C is concatenate. And now, when we run the graph and make it even nicer by putting X labels on there, aha, none, 1, 2, 3. And now this is like our standard, I call that a Borth plot. The header seems a little too big. I'm going to make it a little smaller while you're coding. Tighten it up a little bit. Now, as we talked about before, when you have n equals 3, which is a very small sample size, you've got 1 point at the peak, 1 point at the bottom, and 1 point on the median. But we have to do our doves analysis now with this. Let's take a look. Doves. Let's put this right here. All right, so now sample size n equals 3. Distribution, well, you can't really, this is a normal distribution. It's hard to say n equals 3, but we don't have any skew. You can't really tell if it's skew. We don't have outliers. Variance, it seems to be greater down here. I'm not sure if we're going to pass the equal variance test. Effects, strong effects. This is a staircase. None is the highest. Ding, 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 ding. By the way, this is the exact opposite of what we hypothesized. We hypothesized that 3 inches of compost would be the driest. Instead, or that 3 inches of compost would be the wettest, but instead it's the driest. It's the opposite of what we expect. The soil moisture is lower in 3 inches of compost than it is for none. So that is a bizarre finding. It makes me wonder about how the beds were watered. So it makes me think like maybe the watering regime was very shallow. I wonder who watered it. I did not water it, and I don't think my student watered it either. So anyway, that's a separate issue. But from an effects perspective, which is what you should think about when you first look at this, if you watered it too shallow, didn't water it enough, then the compost is going to catch the water. It's not even going to get to the soil. Then when you sample the soil, it's dry. You need to water. If you water more extensively, you might have resolved it. Otherwise, in any case, we've got a very strong effect, but just the opposite of what we expect. It happens in science. So let's proceed with our process. So first we have to do the Shapiro test for normality, because this is an ANOVA. I should have said this. This is an ANOVA design, obviously, because we're comparing groups, and there's more than 2. So it's an ANOVA process. So you'd have to get out that ANOVA flow chart and work through it, but you know kind of what to do already. Shapiro normality tests here. Everybody's passing, so we're good to go. Looks like you don't have any problem issues with normality. Equal variance Bartlett test, pass that, okay. Then we're just going to do this plot AOV situation. I'm going to sweep this graph, do the par MF row 22, and then run this plot AOV, which we've done before. So you should be able to type up all this code and run this code. I'll just slow down here. Egalitarian sandbox. Would a pencil lay on these points? More or less. This was a little bit bumpy ride here, but whatever. I think we're good to go. So because we've passed the Shapiro test, we passed the Bartlett test, we don't have strong evidence here. Weight of evidence is proceed with a regular ANOVA process, which we would do like this. T equals 0.01. That's less than 0.05. We reject the null hypothesis. Again, type the code, run the code, ANOVA, open parentheses, LM, open parentheses, ag, December 6, dollar sign moisture, tilde, ag, December 6, dollar sign treatment. You should know how to do this already. So this is something we've done in class a lot now. And then we need to compare all pairs using the key process and get our results right here. If we go through these results, you can let me just pull the graph up again. And I actually have already annotated it here. This is the final annotated figure. That jitter's a little bit weird. Again, I think I should make the jitter a lot smaller. 1.5. No. And even less, 1.0. A little nicer. Yeah. So this is the final annotated figure. Type the code, pause the video, run the code. How do you interpret this, or how did I end up building this? Because sometimes this compare all pairs freaks people out. Well, if you go one of these lines at a time, 1 and none. This is none. This is 1. They have the same letter, A. 2 and none. None and 2. They have the same letter. Hey, I went through and did this before, obviously. This is the annotate. I typed all this earlier. Anyway, how to interpret it. 3 and none is right here. Shoot, sorry. Yep. That's none and 3. They have different letters because this is P equals 0.02. So A and B. Now, what about 2 and 1? 2 and 1, the same. They have two same similar letters already. 3 and 1, 3 and 1, 0.057. So this is marginal, but we would round up. 0.06, that's greater than 0.05, so we can't separate those two. So we need 1 to have a B to share that B with 3. Then finally, 3 and 2, 3 and 2, which is these two, 0.679, so they are not different. So they have to share this letter as well. So we've got none is different than 3. But none is not different than either of these two, nor is 3 different than these two. That would be the correctly annotated graph. So what I would like for you to take from this exercise is that graphing your data correctly can lead you to discover errors. And so if you follow through the analysis process using n equals 15 for the treatments, this is wrong. So we caught that and corrected it. How to use aggregate, and we actually did a couple of things up here. We did factor, we did aggregate, we did column names, and we did factor. These are some 3 different kind of commands that it's good for you to know. I also taught you this bit here, which is using GGPlot in a different way. And then how to run the ANOVA process and annotate a final compare all pairs result like this. Of course, we would not publish this graph. We would clean this up and make it nicer looking. But generally speaking, this is the correct way of displaying the analysis results. So I hope that was helpful to you. And take care and get to digging that compost.